The title of this talk is Database Stalls from the Ordinary to the Obscure. I wish I was clever enough to come up with that title, but somebody from the marketing team did that. You can find me on Twitter. That's my handle. I'm happy to answer any questions that you don't want to ask here or that you come up with later on. So this is just a little blurb about VividCortex and what we do. So while you read that, you can sort of pay attention to what I do at the company. So I'm a developer on the backend team, but we're a pretty small company, so I get to do lots of different things. And one of the things that I work on is a feature called adaptive fault detection, which is basically trying to detect stalls in your database. So I'm going to talk a little bit about that. And part of the task of being able to detect those stalls is trying to help people diagnose those stalls. So in hindsight, I think it's really easy to detect those stalls. Mathematically, it's kind of complicated, but the real work, I think, is what happens afterwards. So yes, you have a stall, now what? So this talk is basically all about trying to figure out what to do with the stall, what that actually means, and how you can sort of design your systems to either get rid of those stalls or try to make sure that they don't really impact your systems or your users. So this talk is not about the math. Baron and I co-authored a book with O'Reilly, and we have a book signing right after this session, so go downstairs and pick up a copy because that's all about the math. And if you're interested in anomaly detection in general, I think it's a very approachable book. We do lots of complicated math at VividCortex, but I think we did a really good job of simplifying a lot of that so you can actually implement the things that we talk about. So first off, what is a stall? We talk about stalls all the time, but we have a very precise definition of a stall. And we approach this in a very interesting way. So a lot of anomaly detection implementations, they're kind of looking at like very specific mathematical things, but they're not really obvious to like your specific use case. But at VividCortex, we're just interested in work that's being done. So if you saw Baron's keynote, he's talking about queries, and queries are the actual units of work that the database is executing. So we're basically looking at situations where work isn't being done compared to what was being done as usual. So we're detecting these stalls as short as 1 second long. And we can do this with zero configuration and no fixed thresholds. And the secret sauce is we have a model. And it's a very simple model that you probably already know about. And we're trying to detect these problems and catch stalls before they become bigger, before they lead to lots of back pressure, leading to downtime or outages. And again, at 1 second, you probably won't notice these stalls, especially in your applications. But that's exactly when you want to detect these, because once they become 1 minute or 10-minute stalls, that's when you're actually going to see them, and that's when your users are going to see them. So we want to catch those early on at the low level before they impact anything at your applications or your users. So the model we use is basically Little's law. And we're just looking at concurrency and throughput. So Little's law describes the relationship between concurrency, throughput, and latency. And basically, we use this model to find scenarios when concurrency is high and throughput is low. So if you just think about the database as a little black box, things are going in, work is going in, and work is going out. So in a usual case, work is going in, it's being, something's happening in that black box, and things are being completed, so that usually there's some amount of concurrency in the system, so work is in progress, but the throughput is, pretty constant if there's no variability. Things are going in, things are coming out, concurrency is pretty steady, so that's the best case. When things go wrong, when there's a stall, basically there's a lot of work in progress, and there's a lot of little work being completed. So in terms of metrics, concurrency will be high and throughput will be low. And this maps directly into metrics that are available in the database. So for MySQL, we're looking at threads running. So in MySQL, there's one thread per query running. For different systems, it's a little different, but for MySQL, that's what it is. So because there's one thread per query running, it's really easy to see how many queries are actually being processed within the system. It's just threads running. And for throughput, we're just using the queries completed per second. This is, you're probably measuring these things already. And that's all we use to detect stalls in a system. So here's an example. These are screenshots from the application. Here we have this is actually a pretty significant stall that lasted for 13 seconds. So there's that. We also have a severity, but that's associated with, it's kind of like a z-score, but I won't go into that right now. So again, the metrics that we want to look at are MySQL concurrency here and MySQL queries, so that's throughput and concurrencies up there. And you can clearly see, usually concurrency is around 4 or 5. It's basically a flat line because it's so low. And right when that stall happens, you can see this huge spike in concurrency. And it's a little bit harder to see with the throughput, but there's like a dip in the throughput in the system. And the very common thing that we see is that right after the stall completes, there's a huge spike in throughput. And that's because all these queries are basically piled up within the system. And you can see that in the concurrency. So all of these are just piled up queries that aren't being completed. And once that stall ends, all of them are being completed. So there's a huge spike in throughput. So in terms of metrics, yeah, those are the two metrics. And we're just looking at queries in progress, queries being completed. When there's lots of queries in progress, there's a stall. Once the stall is gone, they all complete. There's a spike in throughput. That's usually what we see. So here's another picture. This is looking at the actual distribution of query latencies. So the total area that you see in this graph is the throughput, but there are different bands that represent how many queries fall into that latency band. So again, this is just a zoomed in picture of what you were seeing before. There's a huge drop in throughput, and once everything's completed, you'll basically see a huge number of queries with really high latency. So most of these, or a lot of these, are over 1 second long because they weren't running during that stall. So that's something that comes up really often. So where do these stalls actually come from? So we're a monitoring company, and we're monitoring, I don't know the exact number, but it's like hundreds of production MySQL instances, and we detect stalls all the time. And these stalls come from, lots of different places, but here are some of the more fancier ones, I guess. Running out of EBS credits. So we actually run our MySQL instances on AWS as well, and we use EBS. Fortunately, we're pretty smart about how we manage the capacity, but EBS is still network attached storage. So you'll actually see microstalls coming from EBS volumes. So we do fault detection on EBS or disk devices as well, and it's using the same techniques. We're just looking at concurrency and throughput. And on Linux, you can get the number of IOs in progress, and you can look at how many IOs that are being completed for that device, and you can do the same sort of thing. The other thing is MySQL query cache. So for a long time, I guess it's still the case, the MySQL query cache has a single mutex. And so, whenever you have a single mutex and lots of work in progress, things tend to pile up because of that. Lock contention, of course, that's kind of obvious. There's lots of different things that can happen. My coworker John actually told me about an example where a bad network cable actually caused pileups in a database. I think it had to do with just network retransmissions and things just weren't getting done, but that happened. It's not something you would predict, but yeah. And the last interesting thing is transparent huge pages. Usually people tell you to turn that off, but lots of times people keep them on, and then we detect these stalls that people don't really notice themselves, and we basically at this point have a checklist. This is kind of like our checklist. whenever a customer says, hey, I have a stall, what do I do with this? We basically go through this checklist to make sure, okay, is the query cache on? Do they have transparent huge pages turned on? Because things like that, you don't really expect, but they can really stall up a system. And eventually, if those things bubble up to your application, you're going to notice it. But if you're not paying attention to some of these metrics, you're going to have no idea how to fix that problem. But the key point is we actually don't really care about any of those. Again, we're focused on the work that the systems are doing. And so oftentimes we detect stalls, but it doesn't really matter for us what the cause is. For the end user, yes, it matters because they want to try to fix these. But again, for us, it's really simple. We just care about the work. Of course, we can do lots of fancy things like actually detecting transparent huge pages or detecting the query cache, or I don't know, somehow we can detect a bad network cable or something. But for the cases of just detecting stalls, it doesn't really matter. We're just focusing on the work. So that gets me into something called work-centric monitoring. So this is something as a company we're really striving for. I've done a webinar on this, but this is basically the entire webinar on one slide, basically. So these are the things that I like to think about when I focus on system stalls and system performance in general. So again, I want to see what the work the system is doing. So for MySQL, it's queries. For disk, it's just IOs. You can think of any system and try to determine what the work that system is doing and focus on that. Because in the end, that's just what they're designed to do. Baron mentioned vanity metrics earlier today. So we want to try to avoid those and focus on the metrics that actually matter. And again, once you do have those metrics, it's important to have a model. Because again, when you have metrics, when you have anomaly detection, it's easy to just throw more complicated techniques on a problem. And it's really easy to get tons of metrics. So right now we have metrics on every single query that's being executed in the system. And of course we can throw machine learning and neural nets or something like that at the problem. But again, it's not really that helpful. It's really helpful to have a model because it's easy to interpret. And for queuing theory and stuff like that, when you're dealing with work, it's really easy to understand what's going on. A couple of the other things are kind of obvious if you're familiar with monitoring, like monitor what you want to optimize, because if you're not monitoring something, it's just a black hole. You're not going to have any insights into that. And I won't go into the other two things. So this is how to respond to database stalls is something that I basically deal with every day, just because our customers find these stalls through VividCortex, and they're like, all right, what do I do now? And depending on the stall, it's super complicated, but I think it's really helpful for everyone to understand what to do, because again, it should be something that you do on your own. You don't have to rely on experts that design the system to really tell you what's happening. So one thing that I learned from Baron is that slowness is about spending time on something. And conceptually, it's really, it's kind of obvious, but it's not obvious when you actually, when you're looking at a bunch of metrics, it's kind of easy to go into a rabbit hole and start finding things that are, sort of strange, or you see spikes in something and you're kind of, diving into that. But ultimately, if something is slow, it's either doing work or just waiting. So when a system is stalled, it's slow. So we're really focusing on if it's doing work or if it's waiting. And there's lots of different things that go into those two things. And I've talked about a few already. When a system is doing work, it's really obvious. And this is actually something that comes up often when you're monitoring things or sending up alerts. Like 99% CPU utilization is not a bad thing. Your system is doing work. And that's kind of one of those vanity metrics. I would never tell somebody to alert on 99% CPU utilization because, again, it's not necessarily a bad thing. If it's running 100,000 queries per second, that's a good thing. It's doing work. We pay for that CPU, and if you're not using it, it's kind of a wasted resource. Again, disk I/O. If something is using all of its disk I/O, it's not necessarily a bad thing because it's using the resources. What is bad is if you know the system can do more work, and that's disk I/O is a bottleneck. And in that case, it's kind of obvious. And there's plenty of other things that I can go into, but you can figure those things out for your own systems. So next, I'm actually going to do a full walkthrough of a system stall and basically how we diagnosed a particular system stall for a user. So in this case, it's actually a little different than what I showed you before. So again, I'm looking at MySQL queries, which is the throughput, and MySQL concurrency. And this is a perfect example of a microstall gone bad. So before I was showing you a 1 second stall. This one is actually a lot worse because you can see it starts off really small. Concurrency just keeps piling up and up and up. This is a really terrible stall because while work is being done, it's just a lot less work. You can clearly see that drop off, but things are just getting piled up. The threads running just keeps going up, and it's just terrible. And again, if you don't solve problems early on, they become really big, and at that point, eventually I think what they did was they just restarted MySQL. They had no idea what to do. Everything was stalled. They just killed it. So one thing that we often look at is lock contention. So when there is a stall, we try to find those locks. MySQL process list is great for that because when there is lock contention, you can kind of see which queries are locking other queries. But we want to be careful about that, so I'll come back to that later. So this is a different stall, but it's, again, showing you the same sort of thing. This is actually showing you a chart instead of that little stall widget. If you're graphing things on your own, you could build charts like this yourselves. If I'm trying to detect stalls manually, just visually, these are the kinds of things that I'm looking for. So the green line below is threads running, and you'll see a short spike with threads running, and at the same time, the throughput, which is this blue or red line here, you're going to see a drop in throughput. And then again, right after that stall completes, you see that huge spike in queries completed. Just a pattern that shows up over and over. And at the same time, I have some more charts of some more interesting metrics. So here's some InnoDB log IO operations. So again, you kind of see that same sort of pattern. I like to think of this as like a heartbeat pattern or an EKG. And that's something that comes up really often. So you'll see something that's pretty steady. It drops down when there's a stall. It spikes up again because all those stalled queries are completing and then goes back to normal. So that heartbeat pattern is something that comes up really often. And here's just a chart showing you query latency. And I think this was a 1 second stall. Becomes really obvious. And again, I can go on and on and on and show you chart after chart of the same sort of thing. There's just a spike. And this is getting to a point that I think is really important. You have to be careful about causality, right? We're observing systems from the outside. And when things happen, we just know the other things that are happening at the same time, but we don't know that causal relationship. So this is, causation versus correlation. This is just that, and we have to be careful about it. So remember, I showed you that MySQL process list locks widget. So if I go back to that, we see this spike in, it looks like there's this particular update that's blocking other queries. The typical interpretation, and this is something that I used to do a lot, was say, oh, here's a query that's doing some locking. That's obviously the problem, right? I have lock contention. There's a stall. Here's a query that's doing some locking. That's obviously the problem. But obviously, I forgot about causality. So if you think about causality, well, it could be the case that this query was just running longer than usual, and it happens to do some locking. So when that stall happened, there's just more instances of this query running, so obviously it stalled itself because of the situation that it was in. So this is not a cause, but rather an effect. So that's something you have to really be careful about. So the alternative is to think about things that aren't really dependent on causality. So this is something that Baron really talked to us about, and I actually learned a lot from just this view. So this is not processless queries, but this is processless states. So this is looking at thread states in MySQL during the time of that massive stall I showed you earlier. So you can actually see the same sort of pattern in this query end state that you saw with threads running earlier. And what we basically interpreted from this is, again, we're looking at thread states. What are these queries doing and what state are they in? So usually when you see something like updating, that's usual. That's normal behavior. When you see something that's updating, it's just doing work normally. So that's not really a problem. And you can actually see instances of the updating thread states earlier before. But query end is actually really interesting because it doesn't actually show up that often. And that's pretty unusual. So again, we don't really know exactly what that means, but it's one of those states that happens at the end of the query execution. And to us, it kind of looks like there's some cleanup involved or something like that. Maybe there's some data structures that are being cleaned up. And because of the fact that this pattern looks exactly like threads running from before, it looks like there's something about this query end state that's causing all of these queries to pile up. And it's not that they're doing actual work, because we've seen other queries do actual work and they're in this updating state, and that's fine. But they're just waiting on something. It looks like they're waiting on something because it's at the end of the query processing pipeline, and they're just kind of piling up. So this is a case where it's actually more complicated than it seems, because now we have to actually ask ourselves, what is MySQL actually doing in that query end state? So this is actually a complicated example, but this gives you an idea of what we're trying to do when we find a stall and what we're looking for. So this actually, I think, is a really important set of metrics to look at. And unfortunately, I didn't really learn about this until recently. So for the longest time, we were trying to figure out, okay, what other metrics and what other charts can I look at to try to explain why the system stalled? But just looking at what state queries are in is actually really helpful. The last thing I want to talk about is back pressure, and I think it's really important. So going back to, so I just want you to keep, this sort of, that sort of graphic in mind. Basically, a lot of queries just piling up, not doing any work, just waiting, because that really ties into back pressure a lot. So back pressure is just about systems receiving more work than they can process. I like to think about like a garden hose example or something, where you have this like fixed size hole and you're just trying to shove more things into it than can fit. And what happens is things tend to pile up behind it. And so again, going back to this example, what I see when I see a picture like this is I just see back pressure. I see queries piling up, and I know that there's actually applications waiting on those queries to end. So when something piles up at a low level, like at the database, that basically means that there are things piling up at the application level. And that might mean things are piling up at the user's level. So thinking about back pressure is really important. And it's really important to handle back pressure at higher levels of the stack. And I'll get to why that is in a moment. So I like to think about this sort of like an onion. So you have clients, and those can be your users using an application, or they can be other systems. And those clients are using APIs of some sort. And at some level, you have your database, and below your database, you have your system, like the operating system or your disks or whatever. And basically, all of the outer layers depend on the inner layers. And so whenever you have a problem in the inner layer, it tends to bubble up to the outer layers. And basically, if you have a problem with the system, for example, the database doesn't really have full visibility into what the underlying system is doing. Basically, all of these, if you're not careful, all of these systems can basically assume that the underlying system is perfect. And so in that case, basically, they just bubble up the problems automatically. So, for example, MySQL might assume that every single disk write will complete in a reasonable amount of time. But when that assumption goes wrong, like if you're using EBS and a disk write stalls, well, it's going to start to stall the rest of the work that it's doing. So here's a hypothesis that I have. It's not really well tested, but we can actually do that testing. My claim is that low-level back pressure can cause unfair slowdowns higher up the stack. And this is not like just a dumb hypothesis. This actually happens in a different kind of system. So this actually happens in TCP networks. So if you have a switch and it's processing a lot of traffic, if there's any sort of if the switch is overloaded and it starts dropping packets, you basically have back pressure because TCP will then start to retry and resend those packets. And now basically what you have is unfair distribution of connections and stuff like that. So this happens in TCP networks, and my claim is that this actually happens as well in database queries and API requests and stuff like that. So I started to think about this, and I think it kind of makes sense when I think about a diagram like this. So I showed you this picture before. This is just, to recap, it's just query throughput broken down by latency. And so basically the redder queries here have higher latency, and the blue ones have a shorter latency. And the distribution kind of looks like this. So if you can imagine just like a 1 second slice of this, this is basically what it looks like. And so there's lots of queries that are pretty fast. There are some queries that are really slow. Maybe you have like a full table scan or something that's taking a few seconds or maybe minutes or something like that. So it's really on the tail end there. And down here, maybe you have like a select one, some sort of like application ping or something that doesn't do any real work, but it's just super fast. So I thought about what this would look like when a system has a stall where there's back pressure. So I just added like a, I don't know, let's say 50 millisecond shift or something. It's not that much. But I just started thinking about what that would do to this distribution of query latencies. And if you just think about query latencies for like really slow queries and then really fast queries, this is kind of surprising. Basically, the fast queries, if you add a 50 millisecond shift, it's not that significant. It's kind of in the noise. If you look at like a full table scan and you have a bunch of occurrences of that and you just add 15 milliseconds, you're probably not going to notice. And the applications probably won't notice. But if you take a fast query that's like 1 millisecond, and I'm assuming like queries that are this fast are probably part of a chain of queries that your application might run as part of like a web page view or something. Basically, if you make that query run like 50 milliseconds slower, that's actually a huge relative shift. That's like 50x. And when something gets 50 times slower at a lower level and you have other things depending on it, again, things bubble up and it gets really bad at the application level. So next, here's some ideas on how to actually deal with back pressure. So of course you can do some rate limiting or throttling at the application level, but I understand this is kind of difficult to do, especially if you don't really know how far you can push your systems. The other thing that you can do is try to use a queue to contain requests at a higher level. So one thing that we tend to see a lot is people running applications written in PHP or something, or Perl, whatever. They don't really have this concept of connection pooling. And so what happens is, I don't know, maybe they're using like each web page view is a separate database connection or something. So when they basically have a bunch of users connecting to their system that maps directly to database queries, and when things start to stall up, the web pages get slower, so maybe the users start refreshing a lot, and they're still opening up new connections and issuing more queries. So basically the connection count is basically unbound. That basically means you're not limiting the amount of work that your database can do. And so, again, going back to that diagram of that terrible stall, that's kind of what I see. The number of threads running keeps going up because they're not limiting it. They're kind of opening it up to user requests, just making the problem worse and worse and worse. So the best thing to do, in my opinion, is to just set a fixed limit on it. And of course, you can do that by setting the maximum number of connections in MySQL. But again, you're not really in control of that, because you're not in control of which connections actually make it into the system and which ones get blocked. And the way to deal with back pressure, the best way, I think, is such that you can actually control what work your system is able to do and what work you can sort of set aside for later. And that's sort of what the third point is trying to talk about. If we had some way to kind of prioritize some work over others, that would be really great. Because again, when you're dealing with back pressure at the edge of the system, it makes for a much better user experience. Because if somebody's just waiting for a page load, it's just a terrible experience for them because they have no idea what's going on. They don't know why things are slow. But if you can say, hey, the system is overloaded, try again in a few minutes or something like that, it's a much better experience for them. But even if you're dealing with your own systems, you're not dealing with actual users, it's much better to prioritize things such that you control the way your system performs, rather than sort of letting things just go crazy and now you're sort of stuck with a system that you can't really control. So here's the important question. Can you eliminate stalls? Probably not all, because you're not always in control of the systems that you use. Again, if you're using EBS or something, there comes a point where you actually can't control the system underneath you. And the best thing that you can do is be aware that the system underneath you can actually stall up at some point. And you can design your applications and your systems to actually deal with that. And one thing that I noticed this morning during one of the MySQL keynotes is the ability to, I can't remember the actual feature, but there's a new feature in MySQL 8 where you can tell it to skip over locked rows and not even wait for locks to be released. So that's, again, going back to dealing with back pressure. So you can actually prevent that back pressure at the lower level of your system and then try to manage it at a higher level. So I think that's pretty cool that even MySQL is adding features to let you do that. So that's all I had. Again, you can find us downstairs, and we'll be doing a book signing and giving away copies of that book. And I'll take any questions. Thank you.